Hello student, welcome to this chapter electricity and magnetism, continuation of the earlier session. So in this session we are studying the theory of Helmholtz tangent galvanometer, and also we will solve some problems. And learning objectives to understand the principle and theory of Helmholtz galvanometer and the concept of uniform magnetic field at the middle of the two coils, and the definition and expression of a reduction factor. All these things we are going to study. Session outcomes. So at the end of the session, we'll be deriving the expression for the magnetic field at the middle of the two coils, and expression and units of reduction factor will be known, and we'll understand the concept through these solved problems. So prerequisites and all these things we should know before going to the theory of Helmholtz tangent galvanometer. So we should know the expression for magnetic field due to a circular coil. This is already done. I have explained in my earlier sessions. So the expression for the magnetic field due to a circular coil is given by this equation. dB is equal to mu naught divided by 2 into Ni divided by L into A square divided by x square plus A square whole raised to 3 by 2. So this is the expression for magnetic field due to a circular coil, and the variation of magnetic field with the distance from the center of the coil. So it is very clear that this x is the distance of the point of reference with respect to the center of the coil. So therefore, it is very clear that as we are moving away from the center of the coil, this magnetic field is going to decrease. So that is the meaning. And in this equation, this mu naught is there. This mu naught is the absolute permittivity of the free space, and this capital N is the number of turns in the coil, and I is the current, L is the length of the wire, and A is the radius of the coil, and X is the distance of our point of reference on the axis of the coil. So these are the things present in this formula. So variation of magnetic field with distance from the center of the coil. So the point is that as you move away from the center of the coil, the magnetic field is going to decrease. And we should know what is the tangent law here. B is equal to BH tan theta. The tan theta is called as a tangent law. So this tangent law comes when a bar magnet or a magnetic needle or a compass is suspended in two magnetic fields which are perpendicular to each other. So here B is there, this is the one field, and BH is there, this is another field. This BH is actually, it is the Earth's horizontal component of the magnetic field. And when a compass or bar magnet is freely hanged in these two fields which are perpendicular to each other, this magnetic compass will align in a direction in which the resultant of this B and BH is present. And also, the axis of this dipole makes an angle theta. The axis of this bar magnet or compass makes an angle theta with the Earth's horizontal component. So this is then the tangent law is given by this B. B is given by B is equal to BH tan theta. where theta is the angle between the resultant magnetic field, or it is also the axis of the compass and the Earth's magnetic field. So that is the meaning. So, and also we have shown here that a couple acts on this compass, and they keep this compass or bar magnet in a direction in which the resultant of these two fields is present. So that is the tangent law, about tangent law. Next, the horizontal component of the Earth magnetic field is BH is equal to B cos theta. So because Earth also behaves as a magnet, a huge magnet, and a plane which passes through the magnetic north pole and south pole is called as the magnetic meridian. And so this magnetic field is divided into two components, one along the equator, one along the geographical meridian. Geographical meridian means it is the plane passing through the geographic north and south pole. So, and this BE is a result, and this BE is the direction of the magnetic field on the surface of Earth at one place, and this is equal to BH is equal to BE cos theta, where theta is the angle between this resultant magnetic field and the Earth's horizontal component. So this is about horizontal component of the Earth's magnetic field. And tangent galvanometer is this is the tangent galvanometer. What is shown what is shown in the diagram is the tangent galvanometer. So what is the difference between Helmholtz tangent galvanometer and this tangent galvanometer? Is that this tangent galvanometer uses only one coil, and at the center of which a magnetic compass is placed, whereas the Helmholtz tangent galvanometer uses the two coils, and at the middle of those two coils a compass is kept. And this tangent galvanometer works on the principle of this tangent law. Next, we'll go to the Helmholtz tangent galvanometer. Let us see what is the construction. A Helmholtz tangent galvanometer consists of two identical circular coils of the same radius and having the same number of turns mounted coaxially on the same base at a distance equal to the radius of either coil. So the two coils are connected in series so that the current through them is in the same direction. A deflection magnetometer or the compass box is mounted at the midpoint of the line joining the centers of the coils. The field at any point on the axis of the coil is equal to the sum of the magnetic field due to individual fields. The resultant field at a point midway between the coils is twice that due to one coil. So, therefore, what happens when there is only one coil? Generally, at the center of the coil, the magnetic field is a maximum. But when there are two coils which are kept very close to each other, then along the axis which passes through the center of both the coils, at the middle of those two coils, the magnetic field will be double of the field due to one coil. So this is about construction. So this is the tangent Helmholtz tangent galvanometer. You see, these are the two coils. This is the one coil. This is the another coil, and these two coils are connected in series so that a same current is passes through both the coils, and also uh, the direction of the current is also same in both the coils. Because of that reason, what happens? The magnetic field created by these two coils will be maximum at the middle. So at the middle here we have kept a compass or a magnet or a magnetometer. It is also called as a magnetometer, or it is something just like a compass. And these two coils are connected in series and like this. So four terminals are there. Two terminals should be joined, and the outer terminals are connected the to the external sources. So this is the construction of the Helmholtz tangent galvanometer. Next, go to the principle. It is based on the tangent law, which states that when two magnetic fields are acting perpendicular to each other, then for a given restoring field, magnetic field, deflecting field is directly proportional to tangent of the angle made by resultant with the restoring field. As I told in earlier diagram, there are two magnetic fields. One is the BH, another one is the B. So at the resultant of these two, B and BH, uh, the magnetic needle will align, and the angle made by this magnetic needle with respect to the Earth's horizontal component is taken as a theta. Then the magnetic field B is equal to BH tan theta. So that where theta is the angle between the resultant field and the Earth's horizontal component. So this is the principle of tangent law. So next we'll come to the theory. Let I be the current passes through both the coils, N be the number of turns, then the magnitude of the magnetic field on the axis at a distance x from the center of the coil of radius a and of n turns is given by this equation. As I just told, this is the expression for magnetic field due to a circular coil, and all the terms I have explained. So here I is the current flowing through both the coils, and if the magnetic field on the line is to be uniform, then d by dx must be constant. That means variation of magnetic field with respect to the distance along the axis of the coils must be constant, and d square b divided by dx square must be 0. So therefore we are differentiating the field equation of a circular coil. So differentiating dv by dx here, we are differentiating dv by dx is equal to d by dx of mu naught n I a square divided by 2 into x square plus a square raised to 3 by 2. And here, so these are all constants, and so the differential operator is kept here. And next, you differentiate, we have to differentiate this equation that gives 3x, actually 3x by 2 into x square plus a square raised to minus 5 by 2. And again differentiating this equation like this, and these are the constants. And so this the differential operator is acting on this. And what happens differentiating that part, so that gives 4x square minus a square, and divided by x square plus a square whole raised to 7 by 2. So this is after second time differentiation. For the condition that dv by dx is uniform, d square b by dx square should be equal to 0. So as this thing cannot goes to 0, so we are keeping 4x square minus a square equal to 0. So therefore I am setting 4x square minus a square is equal to 0, or 4x square is equal to a square, or x square is equal to a square divided by 4, and taking the root, this gives x is equal to plus or minus a by 2. Hence, at a distance of a by 2 on either side of the coil, the rate of change of magnetic field becomes a constant. So therefore, my resultant magnetic field midway between the coils is B is equal to 2 times. If only one coil is there, these two would be not there. As there are two coils, 2 is multiplied here, and it is mu naught n I a square by 2, and 1 divided by x square was there. In place of x square, I am substituting a square by 2 plus a square raised to 3 by 2. And this we have to simplify, and this gives a 8 mu naught n I divided by 5 a into root 5, or you can this equation can be written as a divided by 5 into root 5 into mu naught ni divided by a. The above expression gives a magnetic field at midway between the coils. If Bs is the horizontal component of the magnetic field, then B is equal to Bh tan theta. This already we know. So from comparing equations 3 and 4, as LHS is same, RHS can be equated. I am equating RHS. So this is the RHS. This is equal to BH tan theta. So simplify for I is equal to BH tan theta into 5 A root 5 divided by 8 mu naught n. And you take tan theta outside, right, remaining thing, and therefore I is equal to k tan theta, where k is the thing which is present in this bracket. So this is taken as a k and is called as the reduction factor of Helmholtz tangent galvanometer. So it is very clear that the reduction factor of Helmholtz tangent galvanometer is directly proportional to the Earth's horizontal component and inversely proportional to the permeability of the medium in which the coil is kept and the number of turns in the coil. So as variation of magnetic field between the coils with the distance is shown in the figure. These are the two coils of the Helmholtz tangent galvanometer here, and the horizontal portion of the resultant curve represents the uniform magnetic field between the coils. So here you can see up to from this point to this point, um, the magnetic field is uniform, and at this position, at the middle of this position, here we have kept the magnetic compass or needle. So this gives more accuracy in the measurement. Okay, and so from this point to this point, the magnetic field is uniform. That is why we have kept this magnetic compass in the uniform magnetic field. Whereas in a tangent magnetometer, uh, the compass is kept at the middle of the coil, and the magnetic field is not uniform there. It decreases gradually as you move on away from the center of the coil. Then, what are the advantages of Helmholtz tangent galvanometer over tangent galvanometer? Is that tangent galvanometer has uniform magnetic field only at the center, while Helmholtz has it in between the two coils, and Helmholtz galvanometer is more sensitive. At the same current, at the same time, current in Helmholtz produces more deflection and the magnetic field. So therefore, the Helmholtz tangent galvanometer, which uses the two coils, is more sensitivity and produces more deflection for the flow of very small current. So now we'll come to the problem part. A Helmholtz tangent galvanometer has coils of radius 0.077 meter each, and the number of turns is 49 to root 5. Calculate the current through the coils, which produces a deflection of 45 degree, given that BH is equal to this much is the Earth's horizontal component is given. And you just so we have to substitute in the direct equation. I is equal to bh 5 a root 5 divided by 8 mu naught n into tan theta, and we'll come to know that I is 25 10 power minus 3 amperes. That means 25 milliamperes. Problem 2, again the things are given. Now when there is a second current flowing in the circuit, what happens to the deflection is asked. So this equation is used. I1 is equal to k tan theta 1 and I2 is equal to k tan theta 2, and if we're dividing these equations, I1 by I2 is equal to k get cancelled. It is tan theta 1 divided by tan theta 2, or tan theta 2 is equal to tan theta 1 into I2 divided by I1, and substitute the values, and we are getting theta 2 as tan inverse of 2, and this is 63.43 degree. So this is the deflection. MCQ, the deflection is related to the electric current I in a galvanometer by the relation. These relations are there. The result is that I is proportional to tan theta. So B is the answer. I is proportional to tan theta. A current of 6 amperes produces a deflection of 30 degree in Helmholtz tangent galvanometer. What current will produce a deflection of 60 degree? So this is a small problem, can be worked out separately, and the answer is that B is equal to 1.8 amperes. And going to the MCQ 3, if the number of turns and radius of cross section of the coil of a tangent galvanometer are doubled, then the reduction factor K will become. hmm? So the reduction factor K will become no change. It is not going to change because here the number of turns and radius of cross sections are doubled, so it will not change. The unit of reduction factor of Helmholtz tangent galvanometer is a ampere. And when a current of 1 ampere passes through a tangent galvanometer, angle of deflection is 60 degree. When a current reduces to 1 or 3 amperes, then the value of new deflection will be what is the answer? So the A is the answer, 30 degree. So summary of this session is that we derived the expression for magnetic field intensity, and we derived the expression for current and reduction factor using the tangent law, and I will explain the variation of magnetic intensity with the distance between the two coils graphically, and solve the problems and understand the concept. And these are the reference books you available in your laboratory, and you can go through. So thanks for listening.